Okay, so let's get started. Good. So welcome to a new week. We're continuing our progress through what we need to know about assembly, reverse engineering using the debugger, and how high-level programming constructs map down to really piecemeal, built-up functionality based off of assembly, what the CPU fundamentally can do. So we've got 3 more sessions, roughly, planned around this chapter. So today, it's going to be about how programs implement control flow. So how does a program decide what to do? How does it change its path through a code? All of this is built up incrementally from smaller constructs of comparing data, building out a if statement from where there's also the ability to jump the code to different parts of the assembly. From there, it builds up yet the further higher level constructs we're familiar with, such as the for loop. All of this is based off of the book, chapter 3.6. And this is what you need to know what's going on underneath phases 2 and phase 3 of the bomb lab. Okay, so progress check, right? So who's done with phase 1? Phase 2? Okay, phase 3? Right, so if you want to stay on target, I think you should make a very solid attempt at getting your bomb through phase 3 today. Right, and be prepared for coming back on Thursday, which is going to be the next big concept of how does a program implement functions, right? We spent the first couple weeks of class understanding how the stack and the heap work, how there's these things called stack function call frames. Thursday's class will be all about how the assembly enforces the discipline of what goes on the memory, what goes on in the instruction pointer to create this functionality of function calls and recursion. And then coming back on Tuesday, this will be about how data is stored at the machine level, how data is organized to create arrays and so forth. And that topic on how data and arrays are stored consecutively in memory very nicely leads into the next big chapter of this class, which is about how caches and how memory hierarchy works. Why is all of this important, right? Why is all of this important? The goal is, after seeing all this, you have a better appreciation of how something elementary, something with very limited functionality, such as what assembly language can do, builds up the more complicated functionality in C programming, and especially the topics for next week on how data is organized in the memory. This is stuff that you as a proficient programmer, proficient computer scientist should know to write code that is efficient, right? Write code that works with the computer and how it stores data in memory. Any questions about logistics? Okay, so the first exercise, or the first little example, is picking up a little bit from last Thursday's class. This always gets left over from the lecture on memory addressing modes, which is there's a peculiar example that I want to demonstrate. Again, all of the code examples that you can see for these lectures, they're all in the PA4 directory that you can pull from the repository. I have a bunch of these little demonstration codes that create the examples in the lecture slides. Again, nothing hidden up my sleeves type of, everything is a real example that you can go check for yourself by compiling the code, right? This includes all the quiz examples that you'll see in the quiz. The one that I want to call attention to here is here in this example called 3LEAQ, 3LEAQ example. I've got these 2 functions here. One, who wants to explain what this is trying to do? right? Actually, who wants to explain what this mul add function is doing? What's going to be returned? Yeah.
So it's gonna like take the base, and then there's also gonna be an index where you add like the space for one long, and then you multiply the long space times the index, and then add that value to base.
I think you're overthinking it, right? This is just a number calculation. It's calculating a multiply followed by an add. It's going to just return whatever is specified here, right? 8 times index plus 8 plus base. That's it. What's going to happen with this other function? It's going to return a address location, right? That's the promise of the return type. It's going to be a pointer to a long. And what is that pointer, what is the address location going to be? It's going to be this here, right? So some array called pointer, and we're going to index into that array, and that indexing is going to have 2 parts. One is a variable index, and the other is a constant additional shift, right? So just quick quiz, right? Suppose I have long index as 1. How many bytes farther along than pointer should be returned if index is 1? Yeah. How'd you get 16?
Because the index itself is 1, and so then you would do 1 plus 1, so you get 2, but because you have an array of longs, you multiply it by 8, so you get 16.
Right, so this is an array of longs, so each index along into that array will be, each index is a 8-byte number, right? So this should be returning a value that's 16 in addition to the base, in addition to the pointer, the beginning of the array. So we compile this. So again, you can check all the work, the makefile compiles this, compile it using some additional important flags, one called -s, which ensures that it creates the assembly, -0g, which ensures that it doesn't do any compiler optimizations that change the assembly to be too distinct from the basic C code. And we can take a look at the compiled assembly, leaq.s, and we scroll to where these 2 functions are implemented, right? So there's a lot of visual noise here, but you can see that here is the label for leaq function. Here is the label for mul add function. And the lines that actually do work is this line here, implemented as leaq. And very curiously, multiply add is implemented in exactly the same way, right? Both are implemented essentially the same way, right? And this is kind of a motif for the examples I'll work through, which is I'll give you multiple examples of functions, and underlying them, they all compile to the same assembly code, right? This hints at the compiler is doing something clever to work through this. So let's study what is leaq. So leaq is a pretty fundamental instruction in assembly. What it does is it calculates the address. Right? It calculates the address without dereferencing the address. So it's just calculating what the address is supposed to be. How does this tie to the addressing modes that we talked about on Thursday? So what are the key takeaways about addressing modes from last Thursday? And I get, addressing modes is not the most interesting set of slides, but what were the things that we were supposed to learn about? Yeah.
Basically, the fact that we need to know 2 pieces of information, the data type and how many of that data type we're working with, like data moving through.
So the key point of the addressing mode slides, and you should you should read through it, both my version of the slides and also the textbook's version of the slides. The point of the addressing modes is all these constructs about how arrays are built up, how you index into arrays. All of this is made of the addressing modes, right? Addressing modes have a base, it has a constant offset, and it has a variable offset, which can be multiplied by some multiplier. And that's what ensures that when you write an array, that you're accessing the right number of bytes into the array. So this instruction here, LEAQ, is very similar to the moveQ functions, addressing mode functions, but instead of dereferencing the actual address location, it just only returns the address. So let's take a look at what this slide is saying here, right? So here's the LEAQ instruction format. Both source is going to be written in the format of an addressing mode. So this is the funky base plus offset plus a multiplier format that we had on Thursday's slides. And it will store that calculated address into a destination register, right? It will calculate the value of the address and put it somewhere. So it's useful for determining or getting the return of getting a value, which is the address of something. So here, for example, this C code here is saying that I want to access the ith element of X, but instead of actually getting the array element, what P will be stored to is a pointer, right? I just only care about what's the address of that location. So this gets calculated exactly to this. And it's exactly the source code example I had here of I want to determine the address of some location in the array. So the clever thing here is, like I summarized on this slide here, this function, LEAQ and moladd, both of them translate to exactly the same code on the right, exactly the same assembly. So I've just cleaned up the visual clutter a little bit, right? So here this is saying that both labels for the functions, the snippet of assembly that does work is the same snippet. So why is that, right? Well, the reason is ultimately both functions are calculating the same numbers, right? The actual multiplication that has to take place is exactly the same. And the compiler knows that because memory calculation is something that's so fundamental to what the CPU has to do, the CPU has better capabilities to calculate numbers of this form, right? Anything that could be calculated by the LEAQ function or LEAQ assembly instruction ought to be, right? It's efficient to use this instruction than the much more general assembly instruction called multiply. And so whenever possible, it will use LEAQ to implement that multiplication. Does this make sense? Yeah. So exactly here, right? So this number that's being calculated here, I want to calculate index times 8. Well, index times 8 plus some offset. This form here, index times 8, can it be effectively calculated by this instruction, right? So whereas before, you may want to use imul q to calculate something, if the compiler sees that the number you're trying to calculate is in this form, and it could be calculated using LEAQ, it will. Yeah?
Sorry, which one's the base and which one's the index side of RDI and RSI?
So what's the rule of thumb here? There's a mnemonic, which we haven't introduced yet, but what's the first argument?
The first argument is RDI and the second one is RSI.
Yeah, so there's a mnemonic, which you may see in the next set of slides or in the textbook or in the textbook slides, which is Diane's silk dress cost $89, right? It's a really stupid mnemonic, but it tells you in terms of where each function argument is stored. The first one is going to be in DI registers. The second register is going to be in the SI registers and so forth. So that corresponds to this, right? Base is in RDI, index in an RSI. So this format here, right, recap of Thursday's class, this is an addressing mode calculation. It says take RDI plus 8 times RSI plus another constant 8, right? So it's exactly this calculation here.
And
Yeah.
setting it to is setting it in like that number to be like that address to be an RAX.
That's right, right? They'll calculate what the address of this is and store it in RAX. Right, so this is kind of trivia. Maybe it's kind of trivia. You may encounter something like this in studying your way through Bomb Lab. But the kind of deeper takeaway here is the CPU, right? What the hardware electronic circuitry does to execute instructions. There's varying costs to each instruction, right? And so whenever possible, a good compiler will do reduction in strength. Reduction in strength means to use a cheaper instruction to stand in for a more expensive instruction. Okay, so that's about LEAQ. The next segment is all about control flow, right? Control flow. So first of all, what is control flow, right? Control flow is something that should be pretty intuitive to us. It's when we trace our program, when we're doing our programming, we always have this notion of, well, where is your program, right? What line number is your program at? The program executes in the C source code line by line, right? Always line by line, one line follows the next, except when. What are various situations where, as you're tracing your way through C source code, and it's at line 20, the next line might not be line 21. What are situations where you may change control flow? There's a bunch of examples, right? So we can shout out a bunch of different, yeah. Loops, right? So loops can come back to the top of the loop, or it could end the loop. Another example? If statement, okay. Yeah. Switches is a good example. What else? Function calls, good. What else? I can think of at least 3 more. Yeah.
Break or return statement.
Break, continue, return, good. And what else? Quit or exit, right? Terminating the whole program altogether is a kind of change in control flow too. So all of these things, in assembly, you don't have any of these actual statements, right? The assembly language doesn't define a if statement or else statement. It doesn't define switches. Assembly doesn't have a for loop. Rather, what assembly does have is 1 or 2 types of instructions that can change control flow. And so this whole segment now is about how assembly builds up these useful constructs of if statements, switch statements, loops, and then for Thursday's class, function calls. So let's see. So now we have to zoom back into this view here when we started the assembly chapter about how the machine is organized. So back then, we just focused on just kind of this picture of your program runs in the CPU. All the memory is stored in the main memory. All work has to go through the CPU, right? So we saw on last Thursday's class, for example, there is no move instruction that goes from memory to memory. The CPU is the main character here. All work comes through the CPU. And in the CPU, there's some important things that we need to know. One is the registers. So this is like the RAX register, the RDI register, the register set. There is a notion called the program counter, or the instruction pointer, which points at the memory address where the program is at that moment. And then finally, there was this additional character, which we really have not encountered yet, called condition codes. Right? So condition codes are these registers that store meta information. right? They store kind of side effect information about a calculation, right? And so I like to use this kind of analogy to psychology, right? Analogy to what these correspond to the mind, our minds. So I said how the register is kind of like your consciousness, right? It's kind of the front of mind, short-term, immediate attention memory for performing thoughts. Your program counter, right? What would the program counter be in psychology or in our state of minds? What's it kind of like? Big shrugs. Yeah. So it's kind of like your intent, right? Program counter. It's like what I will do next, or what am I doing now, my conscious of what I'm thinking about now, and what I intend to do next. That's the program counter. So what my condition codes correspond to. Right? Condition codes are kind of our decisions, right? Our decision making about, I thought about this thought, I thought about this other thought, and so my decision is X. Condition codes store decision making information for the CPU. So the way that it does this is there's 4 relevant ones that we encounter in this class, 4 basic types. You can find the full set if you search for x86, the type of assembly that we study. x86, Intel x86 defines the following flags. So you see some of these. There's a whole array, right? And then furthermore, as the x86 got updated to more recent versions, there are now these extended flags. So the 4 that we care about are a subset of these. It's the carry flag, the 0 flag, the sign flag, and the overflow flag. All right, so you'll see there's these 4 here. They're summarized on this slide here. And what they calculate, they're side effect information from any kind of arithmetic computation, right? So every time you add numbers, or any time you subtract numbers, or every time you XOR numbers, all these arithmetic instructions that we've encountered, in addition to setting the target register, they also set these single-bit condition codes. So the definitions are somewhat interesting. It's a whole eyeful. You can read what they're doing. But you can think of these as they correspond to different types of number fields. So for signed and unsigned, they each trigger different types of condition codes. So one such example is the 0 flag gets set if the most recent operation, what's being stored into the destination register, if the value is 0, then this ZF code gets set to true, right? What's a situation that this might be set? Yeah.
You have, like, for example, the largest possible unsigned integer or unsigned whatever, like if you're using it, you either add or multiply that by a positive number greater than 1.
Yeah. So we can devise a pretty concrete example, right? So what's the byte size register? AL. The lower half of the A register is a 8-bit field. If that AL register was holding 255, the largest possible value for a byte, and the instruction you could call is inc byte, increment the byte by 1 bit on the AL register, which is already 255. 255 increment by 1 rolls over, it becomes 0 again, and carry flag will be set to true, right? This is keeping track of overflow for unsigned. There's also the same for sign types, right? So there's a couple other bit fields that store the sign bit and the overflow of a signed type. Yeah, question?
How would you know if it's a positive or negative overflow for OF?
very good question, right? Intrinsically, does assembly code really know about signed versus unsigned? Based off the examples we've seen so far. No, right? In terms of assembly just deals with individual registers, right? And so it can use the RAX register either as a signed long or as an unsigned long. So these condition codes get set no matter what. It's not, so here it says it's applicable to signed and unsigned. Intrinsically, the assembly machine doesn't know if a number is signed or unsigned. It's just going to set these codes based off of assuming that it's signed or unsigned. And it's up to the compiler to interpret these codes correctly. Right? That's a deeper, good question. Any further questions on this slide here? Yeah. So overflow flag, right? So we'll see an example of this in play. We'll study examples. It's better to study in that context. Okay, so condition codes. Condition codes store our decision making, right? The decision making of the CPU. And the way that these things are used is the condition codes are, again, they are side effects of most arithmetic instructions. So one example of an arithmetic instruction is the comp Q instruction. So what it will do is it will calculate the difference between source 2 and source 1. It will perform this calculation, and based off of the result of this calculation, it sets the correct condition codes. So either 0 flag, sign flag, overflow flag, or carry flag. Right, so between these two, taking advantage of comp Q, it can then implement decision making. Right, so here on the left side here, I've got an example code, C code, where what's being returned is an equality calculation. Right, so how might we implement this equality calculation? Right, I want you to kind of think a little bit about whether or not the assembly instructions we've learned so far, add, multiply, subtract, LEAQ, move Q, those types of instructions, could the existing instructions that we've studied so far easily implement decision making like this? Or maybe think about it this way, right? So what should be returned? What are the possible return values here? Yeah. 1 or 0, right? So it completely depends on if they are equal, then sure, return 1. If they're not equal, return 0. So if you think about it, this is neither a kind of addition, multiply, subtract, nor is it a kind of movement instruction. This is a whole different type of calculation that the CPU has to do, right? It's a decision making. Based off the calculation of x minus y, return 2 different possible values, true or false. And this is how it implements it. Right, so first of all function calls, the return is expected to go through the AX register, the RAX register, the EAX register. So as preparation, the first thing it will do is it will zero out the return register, the AX register. How come this implements zeroing it out? So first of all, what is this instruction, XOR L? Any guesses? Yeah.
X will return 0 if 2 bits are the same.
So it's well, okay, answer it this way, right? So in the C source code language, C language, what operator would this be?
Would it be exclusive XOR?
Specifically? Not quite. I'm missing a keyword that I'm looking for. The caret sign? Okay, so what is the caret sign in C? Yeah. Bitwise, right? It's a bitwise is the keyword. It goes through the two arguments bit by bit and XORs them, right? So how come XORing whatever EAX with itself will zero it out? Yeah.
Because if the value is 0, that means it will be set to 0. And if the value is 1, since it's in both, it'll still be set to 0.
Yeah, exactly, right? It's a bitwise XOR, bit by bit. 0 bitwise XOR 0 is 0. 1 bitwise XOR 1 is still 0, right? So XOR is a very convenient way to erase a register. It makes it, zeroes it out. And then the next thing, the instruction compq that we've introduced so far, what it will do, so what does compq do? Compq calculates a difference, so it calculates the difference of x and y, and as a result of this arithmetic calculation, it has side effects, right? So it has side effects. Which side effects is relevant here? So RDI minus RSI, and I care if the result is 0. So which flag do you think is involved? Yeah, just shout it out. Yeah, right? So what's going to happen is compq, this arithmetic calculation, sets these flags. We care about the 0 flag in this case because I want to care if the calculation of the difference is 0, right? And if it is 0, the set equal instruction will set the A register, lower half, to set it to 1 if the 0 flag was set, right? So this layer of things of preparing your instruction, preparing the return register, calculating a difference, which sets a condition code, which then is acted upon by a set instruction, is how you implement this really simple assembly, really simple C snippet on the left. Yeah.
Since any number other than 0 means true, why does it set it specifically to the number 1?
So why just set it to 1? So what other value would you choose then?
Like any value that's not 0 would work, right?
Sure.
Any number besides.
Sure, right? But an elegant choice is that 1 includes true.
So it's like just set E, set will automatically just close to 1 if they're equal. Like,
That's right. Any questions about this slide? Yeah.
So suppose that it wasn't doing the XOR functions in both EAX. What if it was like EAX and EDX, for example? Where would the result? What would we do with the result?
XOR?
Yeah,
You're asking just about this instruction here,
Okay.
right? So what happens? A good question. So what happens if XOR L is not being called on EAX and EAX, which is being how it's used here, but source and des can be different registers, right? So what is the semantics of two different registers passed to XOR?
So I imagine it wouldn't be resulting in 0, but would the result be like parsed into EAX still?
So short answer, right? So XOR L is just like any other arithmetic instruction. It can have a source register, a destination register, and the semantics is the destination register after XOR L will be the original value of source and the original value of dest XORed together. So this is saying like XOR L, A, B. The semantics of it is going to be B equals A XOR B. Yeah.
if you want to keep A and B and have it like go to register C, would you have to first make a copy of B
That's right.
to C and then do XOR of A and C?
That's right. So then what you're saying there is there's a move instruction involved, right? You want to move it to some other destination register, so you move it to another destination register. Yeah.
Just also move is like a copy, right? It doesn't get rid of it from the original register. It's just like basically
Right. Moving makes a copy of the data moving into the destination. Okay, so that's the little translation. And again, you can go to the PA4 repository to see this compilation for yourself. So what we're going to do next is just a few more examples, right? And all of this is actually following the same pattern. If you understand how equality testing works, really the rest of it, same basic idea. What's the basic idea? Prepare the register for zeroing it out. We perform a comparison, which is just a subtraction, and we use the appropriate set bit to look at different condition codes to set a bit, right? So both of these source codes here on the left translate to the same source code on the right, right? So let's take a look at one of the C source codes here. What this is going to do is it will return true if y is the bigger number, right? And assuming that these are unsigned numbers, right? So return true if y is the bigger number. Now I want you to take a moment here, quick thought. Does any of the assembly instructions that we've studied so far, could any of those implement this functionality? Right, we know about moves, we know about add, multiply, subtract, divide, bitwise operations, we know about LEAQ, and now we know about equality testing. You should be able to conclude that, okay, none of the things that we've studied so far can easily implement this comparison of y greater than x, right? So this is a new kind of decision that we have to make. It's a decision-making kind of instruction. I want to return true if, yeah, indeed, y is the bigger number. So the way that this is compiled down, both of these have the exact same semantics, right? To say that x is below y is exactly the same as saying it is not the case that x is greater or equal to y, right? Given that these are integers. So the comparison on the left, both are the same type of comparison. They compile to the right. And here, these two lines are exactly the same as before, right? Exactly the same as the equality testing. But now the decision making is different, right? CompQ is an arithmetic equation, evaluation. It's an arithmetic instruction. It will calculate RDA minus RSI, calculate the difference. And what's the condition codes that we would care about now? Right? This is actually a pretty tricky question. Not tricky, but you kind of have to think about it. Right? The way that it can determine if y is the bigger number, right? Y will be in RSI here, right? The way it will determine if this calculation concludes that y is the bigger number is it has to take a look at if an unsigned overflow took place. Right? In other words, it's going to do this calculation of x minus y, and if x minus y, these are unsigned numbers, so x minus y, x is the smaller number, y is a bigger number. If you do this calculation, it will result in an overflow, right? It will wrap around. The unsigned numbers will wrap around. So it should be a negative number, but it wrapped around, right? It's unsigned. So it will take a look at the unsigned overflow flag to decide if this comparison is the case, right? This makes sense? Yeah.
Why didn't you go to set B to set it? Like, cause doesn't it like just take whatever the last calculation was? And so like, why would you have to do it with the set B instead of just automatically setting the flag?
So the pattern here in this slide, just like the pattern before, right? CompQ, comparison, makes the decision, right? The decision has now been set, right? The CPU at this point has now made a decision that, okay, what is the metadata of this calculation between RSI and RDI. But the decision doesn't enact the return, right? The action that should be taken after the decision has been made is I need to return the decision value, right? And so returning this decision value, the data has to be stored in where the return is expected to be, which is the AX register. So that decision has to be written from your condition codes and put into the return register, which is the AX register or the AL register, right? So they have to enact that decision. So that's where the set instruction comes in to write that decision out. Okay, so there's going to be a whole combination of this, right? So we could go through tedious slides and slides and slides of trying all these various combinations. Okay, I want to show you what x less than y turns into. I could show you what y less than x turns into, and so forth. But basically, it's all going to be combinations of this. I could also show you, for example, what if x and y are no longer unsigned, but rather these are signed types? You know, I can compare signed numbers too. The way all of these are enacted is just a whole different sets of combinations of the set instructions, right? So for all these combinations of signed and unsigned, do I want to determine if it's greater than or equal, above or below, negative, non-negative? There is an appropriate set instruction to do that. Right, so all of these, they're really just reading different combinations of the condition codes that correspond to the right comparison. Yeah?
If I want to compare a signed int and an unsigned int with each other, how would I do that?
So what would be the correct semantics for comparing a signed int and an unsigned int? Does it have valid semantics? It's a good question. I think you should experiment with it. Right? Write a version of this code, turn one of them into signed, and see what it gets compiled to. Yeah. Okay, quick questions so far. Okay, so far this is returning your decision, right? Returning the comparison values. So far we haven't really dealt with control flow, right? We have this ability to compare values now. We still have to have the ability to change our direction through the source code, right? We have to be able to, instead of jumping to the next line of the source code, next line of the assembly, next valid instruction, we have to have this ability to go to another place in the code. And so the next next three sections here are all about control flow after making that decision. There's a couple flavors of this. So there's one flavor, which is to physically change the instruction pointer value, so to jump to another location in the assembly. And then another flavor of this, which is cooler, which is based on conditionally moving data, right? Both of these are important. So the jump instructions are just like the set instructions. You have this whole array of the combinations of them, which corresponds to different comparison values. What's the one that kind of doesn't have a corresponding one from before? Or maybe you got some blank stares here, right? So what's the difference here between jumping and setting? You know, what's the distinction here? I've told you about comparisons, so now I've also introduced sets, but now this is a new thing called jumps. So why are setting and jumping different? Yeah.
Jumping moves you to a different line of code, so sets a value in the correct register.
Right, so jumping takes an argument about where to go, right? It will change the instruction pointer value. It will change which assembly line of code that you're going to be in. Setting was about setting a register value, like setting a register value to 1 for true. Here we have one particular instruction, right? So which one stands out as one that did not quite have an equivalent for sets? Yeah.
Just jump.
Yeah, so here there is one instruction called jump, JMP. Its condition code is always true, right? It doesn't look at any of the condition code flags. It doesn't look at any of the condition flags. It will always jump. So this doesn't really have a corresponding set instruction back here, right? This would be, saying that there's a set instruction which always sets the destination register to 1. That's the equivalent there. So same thing, there's a whole array of these. There's every combination between the condition codes. There's a corresponding jump instruction. And the way that these things are used is a lot like the comparisons that we had before, right? But whereas before, the comparisons were to set a return register to a certain value if the comparison is true. Here, it's going to be a change in control flow, right? So same structure of this slide. So these slides are very dense. So let's walk through them. All of these assembly codes on the left side, and again, you can go to the PA4 repository. You can compile these for yourselves. I've extracted them to all show the information on one slide. All these three instructions, all these three C codes compile to the same assembly code sequence on the right side here. And which one of these three is the most intuitive to read? I'll let you study these three C codes here. Which one is the friendliest looking? Who likes this version? Who likes this middle version? Who likes this third version? All right, most people like this version here, right? And this is how we're used to write C code. This is illustrating that all of these language constructs, they're all really implemented by the same assembly, right? So we can walk through this. The most terse one is this ternary operator, right? The syntax of this is do a comparison. If x is less than y, then return y minus x, else return x minus y. So what's the effect of this calculation? Why would we have a situation we might want to do this kind of return value? Yeah.
To avoid negative numbers, so you would do the largest value, and then that's what you would subtract to avoid like having a negative number.
Good, right? This is returning the absolute value of the difference. Absolute value of the difference, so depending on which is the bigger number, you should take the big number and subtract by the smaller number, which is perfectly equivalent to this middle code here. And it's perfectly equivalent to the third version of code here, which tells us, well, which is implemented in, I would say, a forbidden way, right? Who actively writes code using go-to statements? Have your 111, 112 teachers ever told you don't use go-to? No? Well, we're just not used to it, right? So don't use go-tos, right? It makes for very unmaintainable code, but it is a valid language statement in C, and what it will do is, if this comparison true, then go-to, right? Go-to allows you to define a label in C, and that label says else, and so here is the else code here. Yeah?
Why shouldn't we use go-to statement?
So go-to results in code which is considered unstructured, right? So there's a programming paradigm that we use in C programming and Java programming, right? A style of programming is called structured programming. So structured programming says your control flow should be implemented in ways that are structured. So typically this means if-else clauses, for loops, do-while loops, these things are all structured. But of course, right, you can write totally unmaintainable code where your code just goes to wherever place you want it to go and implement something is correct, but it's a lot less structured, right? So to follow the structured programming paradigm, you shouldn't use GoTo. So all three of these are exactly the same. An important thing is these C functions, if you compile them using a GCC flag called fno-if conversion, right? So this enforces that the assembly will follow the if statements here, follow the if statements structure. All three of them get implemented in the assembly on the right side. And immediately, something is the same, right? So just like before, the comparison is done using the compq instruction. Compq sets the condition codes, and from there, it invokes the jump not below instruction, right? So if not below, right? So if the decision between RSI and RDI is one is not below the other, then it will go to the else label of the code. Otherwise, it just proceeds through, right? So any questions about this? Right, so this is really just the same as before, but now we have this completely new construct of jump, where jump takes a single argument, and it points to a new location in the assembly. This makes sense. Anything I can say here to make this make a little bit more sense? Anything that's not gluing together, anything that's not gelling up? Yeah.
What is the, oh, sorry. It's just the return instruction.
Yeah, so ret is return, right? So this is important too, right? You may ask, so it performs this calculation, stores the value in RAX, and what's preventing it to just continue marching through the code? Well, it's because this return, right? Return will exit back to the previous context. Good. So far we've talked about returning the decision. We've now have an example of changing your control flow based on the decision. And now is finally, well, not finally, the next segment is something of a slightly more advanced topic, which is conditional moves, C moves. Right, so previously this version of code, I compiled it with fno-if conversion. And in practice, most code, you would tell GCC to not have these arbitrary constraints, right? You would typically tell GCC to compile with optimizations, right? So what does it mean for it to have optimizations? What's an example of an optimization I've already shown so far? Yeah.
Would that be like preventing go-to else statements and using one of the other two? Would that be an example?
Okay, so that may be it, but really early, top of this set of slides, right? Top of class today. What was an optimization I pointed out?
Using low effective address?
Yeah, so optimization. So optimization means that GCC, where possible, it will use the cheaper instruction to get the same effect if it knows that this is cheaper, right? So here, the LEAQ whole point of thing was that instead of invoking the expensive imolq general multiplication instruction, it will piggyback off the cheaper instruction of calculating memory addresses to implement the same functionality. So here, GCC, a good compiler, will know that the cheaper way to implement absolute difference, right, this calculation of the greater number minus the lesser number, The cheaper way for it to implement this is through this sequence assembly on the right side here. Right? And this is permitted. We let GCC to now do this version of assembly because we no longer specify no if conversion. So you can also say here, force if conversion, right? So here it will perform if conversion where it can, or more generally, we feed it O1, right? So what is O1, and what does it contradict? So where does this glue together? What is the point of O1 here? What was the opposite of O1 that we've been showing? Or rather, right, some more blank spheres. Where does this go? Where would I put O1? Where does this go? Some blank squares. And any guesses on where this is supposed to go? Yeah.
When you're calling GCC to compile.
Good, right? So we get all these questions, right? GCC. Here's the GCC compiler. The makefile captures what we would feed to invoke GCC. These are all the flags that we control GCC with. So here, in our example so far, they're all specified as no if conversion. And you can also say do if conversion. The versions of assembly we've seen so far have all been specifying 0G, meaning no optimizations, try to preserve assembly, which looks like the source code. And so what I'm suggesting here is instead of providing this 0G flag, we enable O1 optimization. Right? If you turn on O1 optimization, then it will perform compilation and generate this assembly code on this slide. How high does optimization go? Right? So there's many levels of optimization, right? So you can turn on O2, you can turn on O3, you can turn on O4. This keeps going on multiple levels, right? And each higher optimization level you turn on, basically what that tells the GCC to do is think about the source code more and optimize it even further, right? So in practice, you want to have high optimization level. Let GCC do a lot of work compiling the program to create fast and high performance code. Yeah?
So if that's the case with these high level optimization levels, why would you use a lower level one, like O1?
So why are we using 0G right now? Or why would you want to ever use just O1? That's a good question. If you have a very large program, right, you're maintaining source code that's millions of lines of code, compiling can take hours and hours of time, right? So if you're trying to do some kind of rough draft compilation, you may want to turn a lower level of compilation optimization. That's one such answer. Okay, so back to this slide, right? So this version of code, once you enable O1, it instead implements it as this set of instructions on the right. And so what's different now? Well, so what's familiar? The comp Q is familiar still, so comp Q is still here. But curiously, comp Q now takes place after what seems like most of the work has been done, right? So it will calculate y minus x. It will also calculate x minus y. Then it performs the comp Q. And then it moves the correct value into RAX, right? Any questions about why how this implements the same functionality? Or rather, so what's fundamentally new about this slide, right? So who wants to take a guess on what C move B does? This is the secret sauce, right? So any guesses on what C move B does? Yeah.
Does it move if it's greater? Or
So cmove is conditional move, right? So it's just like the move q instructions that we had before, but rather it's now conditional on the correct condition flags, right? So if it makes a decision that this comparison was below, then it will conditionally move rdx into rax, right? So why move rdx into rax? What was rdx and what was rax before? Yeah.
Is x minus
Yeah, so this is saying that by default, rax has been prepared to be x minus y, right? Rax is already x minus y set here on this line here. But if it makes the decision that actually you want to return y minus x, well, y minus x was already prepared in rdx here. And if that's the number that has to be returned, then move rdx into rax, right? And this implements the exact same functionality. So if it's the same functionality, why do this? Yeah.
So if I understand correctly, C move B is reading the result of comp Q.
Mm-hmm.
So does that mean with every like C move B you have to have a complemented conf command as well?
Good question. Should we expect, U after Q, right? Should conditional operators have a corresponding comparison just ahead of it? So what are examples of this? What are the instructions so far where we would typically expect a corresponding comparison to precede it? Or rather, what are the instructions that are dependent on the condition code so far? There's 3 flavors already. What are the 3? Yeah.
One is the jump statements.
The jumps, right? So we've seen so far. Yep. The jumps are always immediately preceded by a comparison. What else? The set instructions, same thing. Set instructions immediately preceded by a relevant comparison, right? And that makes sense, right? Setting, jumping, conditional move, they all will take a peek at the comparison condition codes, and so it makes sense that there is a corresponding comparison immediately before those 3 types of instructions. Good. So why do this, right? Why does GCC think this under optimization level 1, that this assembly is better than the version before here with the branch, with the jump? The reason for this is kind of a preview outside of what's typically covered in 2.11, right? The reason for this is in CPUs, there's this notion called instruction level parallelism, right? The secret here, the thing that we're glossing over in 2.11, is at any given moment, more than one instruction is being calculated in the CPU. Right? Remember, so far I've been telling you, look, in the CPU, there's this thing called the program counter. The program counter is kind of like our current moment in time, right? What are we doing right now? In practice, real CPUs have multiple instructions in flight. This is because the way that a CPU works is each instruction is performed in several stages. First, it gets the instruction from memory. This is called fetching. Then it interprets what that instruction is supposed to do. It will then flip some switches in the CPU so that it calculates the appropriate arithmetic calculation, right? So you get a multiply, it flips some switches so that the CPU will calculate multiply. It performs the calculation, this is called execute, and then after executing, it writes it back to the appropriate location, right? So it performs these operations stage by stage. Now, the next thing you need to know is each of these stages have very little time to execute, right? The signals in these electronic circuits have to propagate from one set of switches, one set of registers, one set of flip-flops, and it has to flow through a delay. It has to flow through logic, Boolean logic gates, AND gates and OR gates and NAND gates, before getting latched into the next stage, right? So these CPUs are designed so that each of these stages takes just nanoseconds of time, right? These CPUs operate at gigahertz frequencies. The signal has to come from here and enter the next stage within a few nanoseconds, sometimes even less than a nanosecond. And so because these stages are so deep, it means that any given moment, there's some instructions that are being fetched, some instructions that are being decoded, some instructions that are being executed, and some that are being stored back to memory, right? This is like doing laundry, right? Why is this like doing laundry? Right? I got some blank stares now, so let's come back to doing laundry. Suppose that you have 4 loads of laundry, right? It's been 2 weeks, right? 2 colors, 2 whites. And you have 3 laundry machines. You have 3 laundry machines. What's the best way to do 4 loads of laundry and 3 laundry machines? Yeah.
You probably want to like equally divide your laundry into 3 machines, but at the same time you have like 2 separate separations of laundry.
All right, so level 1 idea of doing 4 loads of laundry is I load the washer, I wait 30 minutes, take the washer stuff out, put it in the dryer, and wait an hour, wait for the dryer to be done, and take it out and fold it, and then go back to the laundry and load the next washer, right? That's a terrible way to use your laundry machines. Rather, what you would do is once the first load is out of the washer, you put that into the dryer, and already the washer can take the next load, right? This is the same picture here. Here's my washer, here's my dryer, here's the folding stage. And you would keep multiple instructions in flight. Now, if your assembly has code like this, what happens when it hits this instruction? Right? How would a jump instruction like this mess things up? Yeah. Good, right? So once it hits this instruction, you have a jump instruction in flight. Your load of laundry, your pipeline has a jump instruction. What should come next? What should be the next instruction that gets executed? We don't know, right? Because this determination has to be done. We have to wait for the jump instruction to be done to proceed, right? So this instruction here, this jump instruction, holds up the progress, right? It has to wait until jump is done before it can decide, is it this instruction that goes next, or is it this instruction that goes next? And so this version of code is better because you have all of these things in flight, right? This is called speculation. You speculate and calculate y minus x and x minus y at the same time. And then finally, at the latest moment possible, return the appropriate value, right? And so this version of a code better utilizes the CPU. Anything I can clarify here? Did that make sense? Yeah. Sorry, I can't really hear you. You have to speak up a little bit. Last slide? Here. Here. Here.
She said go to the C movement again. C move B.
Here. This is C move B here. I'll go over what a C move B is. So what is C move B? It's C move B is just like the set instruction, just like the jump instruction. It depends on the decision made, right? It's a conditional operation. So it will look at the comparison that took place before it, and based off the flavor of C move it is, this one's the below flavor. You can refer back to this slide here. So the below flavor of these, it will look at just the CF flag, right? What is the CF flag? It's the carry flag. And if the carry flag is set, then it performs the promised operation, right? So it performs move only if the carry flag is set. If the carry flag is set, then it will move RDX into RAX. And what were RDX and RAX so far? So RDX speculatively calculates y minus x. RAX speculatively calculates x minus y. And based off of this decision here of which one's the bigger number, it will replace RAX with RDX if necessary, right? And so taken together, all of these things will result in the C code on the left, the same semantics as the C code on the left, where you return the bigger value between y minus x or x minus y. Good question. Okay, and did that make sense about why this version of code is more efficient than the one that had an early on jump that held up progress? Right? And all of this, so this is our second example of the compiler doing optimizations to better use how the CPU operates. Good. Next constructs. Right, so far we have returning comparison values. So these are the set instructions. We now have control flow, so if-else clauses. And we also have studied a slightly in-depth topic about how real CPUs favor using conditional moves when possible because it permits, it allocates, or it creates more instruction level parallelism. And then the final kind of next topic is, well, in programming that we're used to, we oftentimes write loop statements, right? And technically, what's the takeaway here? If I gave you if statements, could you just use if statements to create loops? So first of all, what are the three flavors of loops? While, do while, for loop. Right? Any more addition than that? That's basically it, right? So if I just gave you the ability to write if statements, you should be able to write for loops. Right? Does that make intuitive sense? Yeah. So if statements, so go-tos, so if I have the ability to write this code, right, I've shown you how this assembly turns into this, I've shown you how this assembly with a go-to turns into this. It makes sense that really this is the end of the lecture already, right? If I know how to write conditionals, we can implement loops, right? But let's fill in the details, right? Let's fill in the details. So the next sequence of slides is yet again several versions of code which are semantically exactly the same as each other. And we start with the one that we're most familiar with, the for loop. Right, so here I have my C code on the left side implemented as the for loop. So here is my for loop, right? And if you think about it, the way for loops are written is kind of unintuitive, right? What are the three portions of a for loop clause? Anybody from back there? Right, I'm asking you to think about all these like deep questions. Like we've written at this point dozens of for loops in our careers, right? Have you really thought about like why does for loops look like that? We're just so used to it, right? So if you think about it, a for loop is really a unwrapped, or rather a wrapped up while loop, right? A for loop has several things. It has initialization, it has a test case, and it has an update clause, right? So this is the famous like int I equals 0, I less than 8, I plus plus, right? There's our for loop right there. Really, each of these separate clauses, you could rewrite them into a while loop on the right side. So things just get shuffled around. I've labeled everything with the green comments to make sure you see how things are shuffled around. So your initialization just takes place as a regular line, right? Set shift to 0. Your test case for the while loop gets moved into the test case for the while loop, right? So there's your test case there. And the final update clause for your for loop just takes place as now part of the body, right? It just is an explicit update that you write out, shift plus plus, I plus plus, right? So are we okay with these two versions of code do exactly the same thing? Makes sense. What will this code do? They do the same thing, but what is the same thing that they do? I'm going to wait until somebody gives it a try. What do these codes do? All right, some leading questions then. First of all, how many times will this code iterate? How many loop iterations will take place? Nine? Yeah. 64, how'd you get 64? Yeah, so here is the test case, right? So this will iterate 8 bits to a byte. How many bytes in a long? 8 bytes in a long. So this will iterate 64 times. What gets returned? Tally. What does tally initialize to? 0. And what is being tallied? What does this line do in the loop body? What are we tallying?
It counts the number of bits that are in the number. Like if it's a 1, then it adds the tally.
Yeah, it counts the number of bits that are 1 as opposed to 0 in your long, right? And you could have figured that out by the name. The name is called count bits, right? So it counts the bits in the long, right? So good, that's basically what it does. Next slide here, same thing. 2 versions of the code, they do the same thing. The left side is just copied over from the previous slide, the while version. But now I've turned it into the do while version. And what's the difference between while loops and do while loops? Yeah.
While loops, they do the shifting, the plus shift plus plus at the end. Sorry, what was I saying? Yeah, they do the operation stuff first for do while. While, like, hold on, let me just make that right.
So
It checks the while statement at the end for do while, but then while, so if it checks them first.
good, right? Do while loops always guaranteed to run at least once, right? And so it's kind of an art to know when your code should use one versus the other, but semantically they can implement exactly the same thing. So I've translated the while loop into a do loop on the right side. Guess what's going to take place next? Another translation. So I take the do while loop, and now I make it unstructured, right? I do a comparison and a go-to statement. So same thing, equivalent versions of code, left side, right side. The right side just gets turned into a go-to statement, right? So notice how on the right side here, there technically is no longer anything that looks like a iteration anymore. There's no mention on the right side here of no fors, no whiles, no do whiles, but still, it's implementing a loop using go-to, right? If you need to loop, go back to the beginning, and there's your loop, right? There's your loop body. Finally, last stage of translation, I've got the go-to version, and that is just a straightaway translation, line by line, into the assembly on the right side, right? And how do I implement go-to? Well, go-to is a comparison followed by a jump, right? Comparison and jump. There you go, right? So we've built up the ability to create for loops, while loops, do while loops, go-to statements by comparisons and jumps, right? And so that's the secret sauce of how really basic assembly instructions in the form of comparing things, jumping, setting bits, conditional moves allow you to build up control flow. Any closing questions? Yeah.
Is that for the XOR in the not that in the AND instruction? Is that a 1 or an L?
Where?
Like it says XOR, and then like is that like after that, is that a 1 or an L?
XOR L, XOR long.
And that's the same for AND, is AND L?
And L, right, that's right. Right, and so maybe kind of tying things together, right? What does this correspond to? What is, how are you being assessed on this idea on the right side? Where does this show up? In the bomb lab, where does it show up? Yeah.
This one shows up, like the looping is in number 2, phase 2.
Yeah, phase two. Phase two is just a for loop, right? The code, the C source code that creates the assembly that you see in phase two looks a lot like this, right? You can go and try to label in the assembly exactly these components of the loop, right? Technically, you're able to reverse engineer the for loop by studying the assembly, and this is the translation process. Okay, so we'll come back on Thursday then.